Predicting the future of a chaotic system sounds impossible, yet neural networks are learning to do exactly that. The authors of this paper tackle a deceptively hard problem, teaching a feed-forward neural network to forecast nonlinear dynamics, not just one step ahead, but hundreds of steps into the future, using only limited training data. Here's why this is hard. Dynamical systems evolve iteratively. Each state depends on the previous one. When a neural network makes a prediction, that prediction becomes the input for the next step. A tiny error at step 10 can explode into chaos by step 100. So how do the researchers fight this error avalanche? The authors test two approaches. The basic model is a standard multi-layer perceptron trained on one-step-ahead predictions. It handles polynomial dynamics beautifully, but for more complex systems they introduce Jacobian-regularization, a penalty term that keeps the model's sensitivity under control. This explicitly fights error amplification, making long-term predictions far more stable. They validate these models on three systems of escalating difficulty. The van der Pol oscillator is a classic nonlinear oscillator. Cylinder wake flow captures the swirling vortices behind an obstacle in a fluid. Buoyant mixing instability is a chaotic, high-dimensional turbulence problem that pushes the method to its limits. The results reveal a clear pattern. For polynomial systems, the basic feed-forward network beats traditional sparse regression methods. But regularization is the game-changer. It extends stable prediction from dozens of steps to hundreds. They also find that strategically sampling training data from a uniform distribution, rather than relying on sequential trajectories, helps the network learn a more complete picture of the attractor. But the method has boundaries. It thrives on systems with low-dimensional attractors, where the dynamics compress into a manageable structure. High-dimensional chaos, like the buoyant mixing flow, still overwhelms the network. The attractor perspective is both the method's strength and its constraint. You can only predict what the training data has explored. Here is the elegant theory behind Jacobian regularization. Each iterative prediction multiplies the previous error by the network's Jacobian. If that Jacobian is large, errors explode exponentially. By penalizing its norm during training, the authors force the network to be less sensitive to small perturbations. The result is transformative. What was exponential error growth becomes manageable. The authors point toward exciting next steps. Data scarcity remains the bottleneck, and smarter augmentation strategies could unlock harder problems. New regularization methods might push stability even further. And ultimately, the goal is not just prediction, but control, using these neural network forecasts to steer real systems in real time. This work shows that neural networks can learn the language of chaos, but only if we teach them to whisper instead of shout. Visit emergentmind.com to explore this paper further and create your own research videos.